Okay. Now we're going to think about our derivative as a rate of change. Um, and we're going to look at two other existence theorems here. So consider the values of a differentiable function. So the key here is going to be that the function's continuous and differentiable. Keep in mind that any functions that are differentiable are continuous, because to be differentiable, the first criteria is that the function's continuous. So if you think back to what it meant to be differentiable. So by saying the function is differentiable, that also means that it's continuous. We still have to kind of state both and be explicit in that. But this theorem that we're going to look at today, these two theorems, mean value theorem and Rolle's theorem. And Rolle's theorem is really just a special case of the mean value theorem. You can get by just knowing the mean value theorem, but Rolle's theorem is a specific case of the mean value theorem. Both of them are existence theorems. And the first thing is we have to have a differentiable function. So we're going to look at graph. We always kind of start off graphically, and then we'll look at how do we do this without the graph. So let's graph the points on this curve. So 0, 1, 5, 2. I'm sorry, 2, 5. I have that backwards. 2, 5, 4, 8, 6, 10, 8, 11, 10, 10, 12, 8. This looks like a parabola. 14, 5, 16, 1. So if we look at that graph, it's differentiable everywhere, so we know that it's a smooth curve. Okay, so we're just going to talk about a couple things here first of all. We're going to look at that the derivative represents a rate of change of a function. Okay, we're going to talk a lot about this now. I know graphically it means tangent line, slope of the tangent line, but we're going to talk about that it means the rate of change, and that could be visually represented with a tangent line and talking about the slope of that line. But rate of change is slopes. That's what we want to think of. Okay, rate of change is slopes, even without the graph. And what we've been doing kind of before calculus is average rate of change. But now with calculus, we have also the instantaneous rate of change. So the two types of rate of change are going to be the average rate of change, which that is the slope. They're both slopes because they're rate of change, but the average one is the slope of a secant line on a given interval. So we're going to say on the average rate of change would be on the interval, closed interval, the average rate of change is defined as the slope of the secant line of the endpoints, right? So I take the y value from one endpoint and subtract the y value of the other endpoint. Then we subtract the x's. This is our average rate of change. It's the slope of a secant line on an interval. Our instantaneous rate of change, since it's a rate of change, it's still the slope of a line, but it's going to be the slope of the tangent line, which we know to be the derivative. So, and it happens at an instant, so I don't need an interval. That's the magic of calculus. You can find the rate of change at one point, which previous to derivatives, that was impossible. To find a rate of change, we needed 2 moments in time, and what we were really doing was the average rate over that time period. So we're saying at a single value, x equals a, the instantaneous rate of change is defined as the derivative evaluated at that moment, at that x value, f prime of a. Remember, that's different than f prime of x. f prime of a means we have f prime of x, and we're plugging that point, that x value a, into the derivative. That's the instantaneous rate of change. So we're going to do that for, we're going to do the average rate of change for that graph we have above on a given interval from 2 to 12. So we're going from 2 to 12, right? So we're going to do the average rate of change from 2 to 12. So that's going to be at the point 2.5 and then 12.8. And think about, it's really the slope of that secant line. Right? So the way that we do this is we do f of 2 minus f of 12 over 2 minus 12. We did y minus y over x minus x. Negative 3 over negative 10, which is 3/10. So that is the average rate of change over the interval, 3/10, rise over run. The instantaneous rate of change, well, we can't find what it is because we don't actually have the equation, and this is not a linear section of a graph where we say, like, if it's linear, I could at least I know the rate of change is the same everywhere on there. So we don't really know what it is. So what we're going to do is just, is the instantaneous rate of change at 4 greater than the rate of change at x equals 6? We're just going to kind of compare those two rates of change. So if I draw at 4, x equals 4, the instantaneous rate of change, is that what we want to do? Yeah, at 4 versus at 6. So here's an x value of 4, and then here's the slope at an x value of 6. Which one has a steeper slope? 4 has the steeper slope. So they said, is it greater than at 6? We're going to say that it is greater. So we'll say the instantaneous, whoops. So the instantaneous rate of change at 4, which is f prime of 4, is greater than, that should be a, then the instantaneous rate of change at x equals 6, which is f prime of 6, because the slope of the tangent line is greater there. You can just visually see that. So we're going to look at our first theorem, Rolle's theorem, and we're starting here, but remember, it's just an application of the other theorem we're going to learn, the mean value theorem. But let's start with the Rolle's theorem. So first of all, f of x has to be continuous on the closed interval, and it has to be differentiable on the open interval. If those two things happen, and so this has kind of 3 criteria to start off, and the y value of the endpoints are the same. So remember, f of a means the y value of the first endpoint, and then f of b is the y value of the other endpoint. If they're equal, they're the same height, then there must exist, so again, it's an existence theorem, at least one value we'll call it C on the open interval. So it's not one of the endpoints. some other value that's not an endpoint, such that the derivative is equal to 0. Such that its derivative is equal to 0. Meaning it will have a horizontal tangent line. Graphically, this makes sense, because what we're saying is we've got a function. Let's say there's two endpoints, and their heights, their y values are the same. So they're the same height up. And it's got to be continuous and differentiable. So what we say is that somewhere on the graph, there has to be a horizontal tangent line at least once. Here on the one I drew, it occurs 3 times. And what it's really saying is that's because if you do the average rate of change on the interval, if I do it for the endpoints, since their heights are the same, I get the average rate of change over the interval of 0. So that means that the instantaneous rate of change somewhere on the graph at least once has to equal that. And that's really what mean value theorem says. Rolle's theorem is sort of the application, a specific case of that where it's actually 0. So let's consider the function from the previous page. Does Rolle's theorem apply to the following intervals? Explain why or why not. So first on the interval from 2 to 14. So if we look at the interval from 2 to 14, we're looking at, let me erase what I have on there already. From 2, which was, what was the x value? 2, 5. To 14, 5. So if we're looking on this interval, is the theorem, Rolle's theorem, applicable? The answer is yes. Let's write why that is. So first of all, is the function differentiable? Is it continuous? We have to prove that or state that. So since f of x is differentiable and continuous, so we want to say that it's continuous also. So it's differentiable on the open interval 2 to 14. And it's also continuous on the open interval. We're just going to say that it's actually differentiable because we know the graph goes past 2 to 14. We're going to say it's actually differentiable on the closed interval, which means it's also continuous, because wherever a function is differentiable, it's continuous. Because differentiability implies continuity. So we talked a little bit about that. And the y values of the endpoints are equal. They're both equal to 5. Then Rolle's theorem is applicable on that interval. That means there will be some point on 2 to 14, the open interval, 2 to 14, there'll be some x value where the slope of the tangent line is 0. So there will be a horizontal tangent line at least once. How about the interval from 2 to 10? So that interval, oh, and again, we should probably just point out, we were doing from 2 to 14. Notice that the y values are the same. Now if we go from 2 to 10, the y values are not the same. So Rolle's theorem will not be applicable. So we'll say, although we want to still kind of practice stating the first part, f of x is differentiable on the closed interval, which also makes it continuous. So we'll say differentiable and continuous on the closed interval 2 to 10. The endpoints do not have the same height. They have different heights. So Rolle's theorem is not applicable. So let's look at these below here for each of these functions. Let's see if it's applicable, and if it is, let's apply it to find the theorem to find the C's that are guaranteed to exist. So remember, we're doing two things here. If Rolle's theorem is applicable, the theorem itself just states that there is a C that exists. Then outside of the theorem, they want us to go find that C anyway. That's sort of a different question. So we're going to say that, first of all, let's look at the endpoints and make sure they're the same. So g of negative 3, when I plug that in, I get 9 negative 3 squared minus negative 3 to the 4th. That's going to be equal to 0. And g of 0 is equal to 0. So there we go. We've got the same y values for our endpoints. So that means it will work as long as it's continuous and differentiable. Well, g of x is a polynomial, so that's continuous and differentiable for all reals. So we're going to say since g of x is continuous on the closed interval and differentiable. I know I'm saying it differently than before. I'm just showing you different ways you can say it. On the open interval, and the y value of our endpoints of our closed interval are equal, then Rolle's theorem is applicable. That's all the theorem says. It states that there is an x value. There's an x value on this interval for which the derivative will be equal to 0. Okay, so now they want us to find what that value is. So I'm going to find the derivative at c is equal to 0 for some y value, right? So we're going to start by taking the derivative of g. So g of x is what? 18x minus 4x cubed. And we're going to say that there is some c. So since they talk about c, we'll use c's instead of x's, where it's equal to 0. So 18c minus 4c cubed equals 0. How do we solve that? We're looking to factor. I can factor out a 2c. So I get 9 minus 2c squared equals 0. So 2c equals 0, and 9 minus 2c squared equals 0. So I'm going to get c equals 0. And then I'm going to get, let's see, 9 equals 2c squared. So c squared equals 9 halves. So c equals plus or minus the square root of 9 halves, which is 3 over root 2. Sorry, I'm out of a little room, so I'll do it up here. C equals 3 over root 2 and negative 3 over root 2. Let's see, the c's that are in our given interval they want us to find. So our interval was from negative 3 to 0. So we're going to get, we're going to throw this one out because the endpoints don't count. The Rolle's theorem is on the open interval, so 0 is no good. And then negative 3 over root 2 and positive. Well, the positive 3 over root 2 is certainly not on this interval, but the negative 3 over root 2 is. So that's the c value that's guaranteed by Rolle's theorem. At that x value, we have a horizontal tangent. Let's try it with number 2. So I look right away and I say from negative 4 to negative 1, I see a denominator here, and negative 2 makes the denominator 0, which makes g of x undefined. So g of x is undefined at negative 2, and negative 2 is on the interval, so we can't apply Rolle's theorem. So we're going to say since g of x is undefined at x equals negative 2, which is on the interval negative 4 to negative 1. So it's not continuous on that interval. Then, so we'll say then g of x is not continuous on the interval. And Rolle's theorem does not apply. So it will not guarantee a value of c such that, just to practice stating the theorem, You could just say does not apply. It does not guarantee that. So there will be no C where the derivative is equal to 0. So here is an official kind of statement of Rolle's theorem. So you can take a second, pause the video, and read it. Now let's look at the broader theorem, the mean value theorem. The mean value theorem it states, right, mean we have to think average. So what we're doing is we're finding the average rate of change over a given interval, and we're stating that somewhere on that interval there has to be an instantaneous rate of change that has that same average rate of change. So we'll think about it graphically first, as always, but I wanted to look at Rolle's theorem. So Rolle's theorem is the same idea. Like if we look back at this first one where it worked, right? That's my average rate of change if I find the slope of that line through those two endpoints. And if the average rate of change equals 0, then that means somewhere on this interval at some point the slope of the instantaneous rate of change, or the slope of the tangent line, has to be equal to the slope of the secant line. And that's Rolle's theorem. Mean value theorem says now it doesn't have to just be 0, because Rolle's theorem makes those y values of the endpoints be the same height. Now if I look at, say, this value here, these two endpoints, I've got a slope that's clearly not 0. But whatever that slope is, there is some point somewhere on the curve where, I don't know, maybe it looks like it's right here, where if I draw that tangent line in, it's going to be parallel to the average rate of change, my instantaneous rate of change. It's saying somewhere on the interval you will hit that rate of change. And it makes sense. This is a theorem that had New York State considering giving speeding tickets based on their checkpoints when you go through Easy Pass. If they know when you go through one gate on Easy Pass, and then they know when you go through another one, they can calculate your average rate of change over that time. And by the mean value theorem, they can say if your average rate of change is over the speed limit, let's say 75 miles per hour, they know at some instant over that interval you had to have it gone at least 75 miles per hour. If your average was 75, then you had to hit 75, provided that that graph of your speed is continuous and differentiable everywhere. So that, of course, didn't work because they didn't end up passing that because no one would use Easy Pass if you would get speeding tickets. But I know that they considered that. So we're talking about the average, comparing the average, or starting with the average and then talking about the instantaneous rate of change over an interval. So let's get our theorem down here. If f of x is continuous on the closed interval and differentiable on the open interval, then there must exist a value, we like to call it C, on the interval. Again, we're not considering the endpoints. So on the open interval AB, such that the instantaneous rate of change, which is f prime of C, remember that's the instantaneous rate of change, which is really the derivative at a certain x value. So at that x value, the derivative has to be equal to the average rate of change. So that's going to be the slope. The derivative is the slope of the tangent line at a certain x value is going to be equal to the slope of the secant line, or the average rate of change over that interval. So this represents our average rate of change. All right, so let's look at this. Consider the function shown on the graph below. Does the mean value theorem apply on the interval -1 to 5? Explain why or why not. So it looks like we have a at 0, we have a vertical asymptote, which makes it not continuous. So we're going to say that the mean value theorem, oh, whoops, I'm up here. The mean value theorem does not apply on the interval -1 to 5 because h of x is undefined at x equals 0, which makes h of x not continuous on the interval. The closed interval, -1 to 5. Does it apply on the interval 1 to 5? Well, now let's look at that. Whoops. From 1 to 5, yeah, it's going to apply. The function's continuous and it's differentiable. There's no cusps or anything. It's differentiable on the open interval. So we're going to say h of x is continuous on the interval 1 to 5 and differentiable on the open interval so the mean value theorem is applicable on 1 to 5. Graphically, what does the mean value theorem guarantee for the function on the interval 1 to 5? Draw this on the graph to the left. So what it's saying is that on this interval, the average rate of change is given by that secant line. That's the average rate of change if I did the slope of the line that passes through those two endpoints. The theorem is saying that somewhere on this curve, at some point in this interval, it looks to me to be like, if I had to guess, maybe right there, that if I draw the slope, if I draw the tangent line, that slope or that rate of change will be the same as the secant line. Remember, rates of changes of lines are slopes, and slopes are equal when lines are parallel. So maybe I back that up just a little bit because mine doesn't look so great there. It's not exactly parallel, but I also probably didn't draw it perfectly. So what we want to say here is that the mean value theorem guarantees a value of c between x equals 1 and x equals 5. Again, not the endpoint, so on the open interval where the slope of the tangent line, i.e. the derivative at that value, is the same as the slope of the secant line over that closed interval. Which would be given as h of 1 minus h of 5 all over 1 minus 5. So there exists some value in there where the slope, the instantaneous rate of change, is equal to the average rate of change over the interval. So they want us to apply the mean value theorem to find the values of c guaranteed on that interval. So we had our h of x. They gave us the equation. So now we're actually finding what that value is. This really isn't the theorem. The theorem just says one exists. Now we're going to apply it to find out what it is. So if I do the derivative, I get 5x to the -2. So there's going to be some c where that derivative, which I'll call it c squared, is going to be equal to, so that derivative, there's some c, that's going to be equal to the average rate of change on the interval, which was h of 1 minus h of 5, all over 1 minus 5. So I'm going to solve this for c to find that value that's guaranteed. Negative 2 minus 2 over 1 minus 5. So 5 over c squared equals 1, right? Yeah, so then if I cross multiply, I get c squared equals 5. So I get c equals plus or minus root 5. And we're talking about the interval from 1 to 5, so I can throw, right around 1 to 5, I can throw out the negative root 5. So it's going to be the c is going to be positive root 5. If this was a calculator exercise, I guess it would be 2.236. All right, so let's move on here. Explain why you cannot apply the mean value theorem for this function on that given interval. So since we have f of x is x to 2/3 minus 2, that means that at the x value 0, because it's a 2/3, I know that a spike or a cusp occurs at the x value to the 2/3. So at x equals 0, we're going to have a spike there. So the function is not going to be differentiable there because f prime of x is undefined. So the reason I sort of know that is I kind of just think ahead to the derivative. Whenever this power is less than 1, when I reduce the power by 1, I'm going to get a negative power, which is going to put the x in the denominator, and that's going to cause a problem for the derivative. So if I do the derivative, I get x to the negative 1/3. And then I know that can be written as 2 over 3x to the 1/3. So now I know when x equals 0, f prime of x is undefined. So I can say f prime of 0 is undefined, which means the function is not differentiable at 0. So I will say, since f prime of x is undefined, I got to say why I know it's not differentiable. I just can't say it is, which is on the open interval. This means that f of x is not differentiable. On that open interval. Hence, we'll use the hence here. MVT is not applicable for f of x on the closed interval. Okay, so now they want us to find the equation of the tangent line to the graph of f on the open interval 0 to pi at the point which is guaranteed by the mean value theorem. So first, on the closed interval, I have to, well, the graph is continuous and differentiable everywhere because sine of x and I add 2x to it, that's continuous and differentiable everywhere. And they're not asking if it's guaranteed. They're telling you it is guaranteed. So they're saying the mean value theorem applies. Let's find the equation of the tangent line there. So first we got to find out where is the x value on that interval where the slope is the same, the instantaneous rate of change is the same as the average rate of change. Once I find that x value, then I want to actually write the slope of the tangent line, the equation of the tangent line at that point. So first of all, let's find out what the average rate of change is over that closed interval. So if I take the endpoints, because they don't want us, right, they're saying open interval because they just want us to find the point on the interval not being one of the endpoints. So if I do f of 0, I get 2 times 0 plus sine of 0 plus 1. I'm getting 1. And then f of pi, I'm getting 2 pi plus sine of pi, which is 0 plus 1. So I'm getting 2 pi plus 1. So if I do the average rate of change on that interval, I'm going to do f of 0, 1, minus f of pi, which is 2 pi plus 1, excuse me, all over 0 minus pi. So, simplifying, I get 1 minus 2 pi minus 1 all over negative pi. So I get negative 2 pi over negative pi. That's going to actually be an average rate of change of 2. So now the instantaneous rate of change on the interval will happen at the derivative. So we want to find the c where the derivative equals 2. So if I take the derivative, let's look at it this way. I like to use the c because that's what it says in the theorem. So my derivative is going to be 2 plus cosine of x. So there's going to be a c. So f prime of c is going to be 2 plus cosine of c. So there's going to be some spot c where the average rate of change is equal to the instantaneous rate of change. So I'm going to say 2 plus cosine of c is going to be equal to 2, the average rate of change, right? So now I can solve this for c. I get cosine of c equals 0. So c is going to be equal to pi over 2. Because remember, it's got to be on this interval 0 to pi. So I know that the cosine, the angle for which the cosine value of c is at 90 degrees, which is pi over 2. So that is the spot where the instantaneous rate of change, i.e. the derivative, that's the x value where the derivative equals the average rate of change. So we already know the slope of our tangent line. They want us to write the equation of our tangent line. We know that it's 2 because we just found the x value so that the slope of the tangent line was equal to 2. We know that our point of tangency is pi over 2 because we just found the x value where that happens, something. So how do I find the y value? I got to plug my pi over 2 into the original function f. So we've got 2 times pi over 2 plus sine of pi over 2 plus 1. So this is going to be equal to pi plus sine of pi over 2 is 1 plus 1. So it's going to be equal to pi plus 2. So that's our point of tangency. So if we write the equation of the tangent line, it's going to be y minus pi plus 2. You got to put it in parentheses. Equals the slope of x minus x. And there's the equation of our tangent line. Just an official reminder of our mean value theorem. You can, there it is typed out. So you can pause the video and look at that, read it, write it down, whatever you want to do.